We're going to introduce you to some scientific notation, and it's a logical extension from the work we've done to do with our powers, because we're looking at powers of 10. So times we're dividing by a whole bunch of tens. So look here, we've got the Hoover Dam, which is in the interior of the United States, and it was one of the biggest, for a long time, one of the biggest concrete structures ever made, and still is huge. And the volume of concrete used is a big number there. That's the number of cubic meters of concrete used for the Hoover Dam, which dams the Colorado River, I believe. And that's 3,400,000 cubic meters. That's a big number. And when we write big numbers, it takes a lot of zeros, and occasionally, if we're not careful enough, not only does it take a long time, we can actually write an incorrect number of zeros down because it's a lot of digits. The mass of a molecule of water is apparently that mass in grams. So 1 gram is, maybe like a grain of rice or a grain of salt, but that's a tiny fraction, tiny fraction of a gram. And again, in terms of efficiency, writing it like that has some problems because it takes a long time. It's a hassle to write down. Very easy to make errors there. So is there a better way? Well, yes, the better way is scientific notation, as you can see. So let's have a closer look. We use scientific notation whenever we've got very big or very small numbers, and for a long time we've had need for this, and the need keeps increasing in our highly technological world. In the era of nanotechnology and space exploration, we keep having a bigger and bigger need for scientific notation. Let's see how we can deal with the conversions. The basic form of numbers written in scientific notation follows some rules, and the rules are written here. Let's have a look at the first rule. So numbers written in scientific notation are expressed in this form here. Now what that means is that the first number has to be between 1 and 10, but not including 10. It's got to be less than 10. So the smallest it can be is 1, and the biggest it can be is something less than 10. Or it can be the same but a negative. So it can be negative 9.999 and up to negative 1, or it can be from 1 to 9.999 positive. Now the m here, that little index, is an integer, which means a whole number that's positive or negative. It can be positive or negative, but it's a whole number or zero, but it cannot be a fraction or a decimal. So the m must be an integer. It's important. So make sure you understand the form, otherwise you're not writing in correct scientific notation. Large numbers will use positive values of m, so the m will be a positive. That m will be a positive if it's a large number. An example is 38 million. If we have 38 million years, that's an expanded form or standard form. To write that in scientific notation, what we do is we take a little journey. Now when we write 38 million, the decimal is there where you see the red dot. If we're turning it into this form here, where a is some number between 1 and 10, we make sure there is 1 digit to the left of the decimal place when we're finished. That means we're moving this many places: 1, 2, 3, 4, 5, 6, 7 places. We've moved 7 places and we get the number 3.8. Now for 3.8 to have the same value as 38 million, well, it needs to be multiplied by 10 to the power 7, which is 10 million. So that's where that 7 came from before. The thing you've got to understand about scientific notation and the expanded form is that this and this number, even though they're in different forms, they have the same value. Of course they do. But some people don't realise that. They think we've changed the number, made it bigger or smaller, but of course they're the same number, they have to have the same value. It's just that it's a different form, perhaps a more efficient form. Okay, so it has the same value but a different form. So 38 million years is 3.8 times 10 to the power 7 years. Small numbers, we follow the same thing. 417 nanoseconds is that many seconds. And nano means times 10 to the negative 9, 1 billionth. So if we follow that same process, we need to remember it to be in the form A times 10 to the m, where A is between 1 and 10. Well, that means that we're going to have the first 4 there to the left of the decimal and the other digits to the right, and then times it by a power of 10. So 1, 2, 3, 4, 5, 6, 7 places again, but it was in a different direction. So it's 4.17, and to get it to be very small, we have to times it by 10 to the negative 7. You can see the negative there. Why is it negative? Well, think about the negative index law. 10 to the negative 7 is a very small number, because you know that it's 1 over 10 to the positive 7. And that's 1 over a very big number. Okay, so that makes sense. If we times 4.17 by that very, very small number, you get a very, very small number of nanoseconds. Lastly, 2 quick examples. So we're looking at the form A times 10 to the m. That means A's got to be between 1 and 10. The way to get that is to have a 4.5. There must be 1 digit to the left of the decimal. To change 4.5 into 4.5 million, we need to times it by a million, or 1, 2, 3, 4, 5, 6, 10 to the 6, and that's our answer. This one, we're expecting a negative index, so it'll be times 10 to the negative something. And to get that A value between 1 and 10, the decimal is going to have to look at the decimal there for this part here. So it'll be 4.0. Notice the 0. 4.0 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 times 10 to the negative 7. So big numbers have a positive value for m, and small numbers have a negative value for m, like we saw up here. Try some.